Hello, Chem 2 students. Mr. Keister here with you again. This is the video for Thursday, October 15th, 2020, which is our scheduled 40th day of school for the fall semester. Wow, 8 weeks. Whew, 8 weeks in. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at today's schedule, our do nows. So we're going to pick up our new notes back today for Unit 3.2 and also an assignment over, actually it's mostly a review assignment over electron configuration. You're also going to pick up your first quarter binder checklist. We'll talk about that in a minute. I haven't finished grading your exams from Unit 3.1 yet. Hopefully you'll have them back in the next few days once everyone has taken it. I have a few people that haven't taken it yet. Your homework for today will be to complete the assignment that you picked up today. I'm going to briefly begin Unit 3.2 regarding the history of the development of the periodic table and what we've learned about it so far to help you get started on the assignment. And lastly, your fall semester quarter one review, which was handed out last week, is also due today by the end of the class. All right, it's worth a lot of points, about double what a normal test is worth. So. And again, no answer key provided for that, so make sure you put forth your best effort on it. It can be a real grade changer. I would highly suggest, and I mentioned this before, that you check your work with other classmates before you turn it in. Maybe you'll catch some mistakes you make along the way and be able to fix them before you turn it in. Your binder, your first quarter binder is due by the end of class tomorrow, and I will be collecting that for a grade. Turn it in any time between now and then for me to check it over. Paper's got to be in order according to the list. All right, according to the list. So let's go to the notes for just a few minutes, and then we'll get started on today's work. Also, then hopefully you can check over your big review packet before you turn it in. All right, so I wanted to give you a brief history of the periodic table. You might want to get it out. We're going to be looking at it here in just a little bit. So the first person who really put together a chart of the elements was a German by the name of Johann Dobereiner. This was done in 1817. He called his chart the law of triads. All right. He noticed that there were groups of threes such as lithium, sodium, potassium, and fluorine, chlorine, bromine, in which the middle element had properties that were the average of the two elements above and below it. So he put together a simple chart that had vertical groups of threes in it, all right, where certain properties he put on the one end, and as the properties changed to different ones, he laid those out on the other end. So basically the way the periodic table is now, but of course there weren't that many elements then. The next attempt at revising that chart of the elements was by an Englishman named John Newlands. He laid out his chart and called it the law of octaves. He composed a periodic table in which he placed the 56 known elements at that time in 11 vertical groups based on similar properties. And notice that many of the elements in a group had masses that were some multiple of 8 of another element in that group. Interesting. 5 years later, a Russian chemist by the name of Dmitry Mendeleev, this is a name you probably already know, he is called the father of the periodic table, and hence the name periodic table actually came from him. By now we had 70 elements, so between 1864 and 1869 we jumped from 56 to 70. He listed them in vertical columns in order of increasing mass, average atomic mass or molar mass. He noticed a regular periodic recurrence of their properties, both physical and chemical. He arranged the columns so that the elements with the most similar properties were side by side. So very similar to what Dobereiner and Newlands did, but now, just a little more extensive way. His most famous work was he left blank spaces where no known elements existed with those particular properties, and boldly predicted that elements would be discovered and be put in those places. At that time, people thought, yeah, right, whatever. But what he did was really pretty ingenious. So here was one of his columns. And So this element had been discovered and this element had been discovered. They were similar in properties, of course. And this one had a molar mass slightly larger than this one. And then the next one did as well. And then all of a sudden he had one that seemed to match up with the properties of those, but its mass was much larger. And so he thought, well, it doesn't make sense that it would be here. It's probably one below that. And so there's some element here that we haven't discovered yet, and I think it's going to fit in there. And like I said, people thought, yeah, okay, sure. But then, and he predicted that there would be elements there at some point. Unfortunately, he died before he was able to, for people to understand just how smart of a prediction that was, because eventually elements were discovered that filled those spots right here, and so all of a sudden made him look pretty dang smart. Although he didn't live long enough to really get the credit that he truly deserved. Okay, and then the final revision of the periodic table occurred by Henry Moseley in 1913. He determined using an X-ray tube, X-ray diffraction, that atoms have definitive atomic numbers. Okay, so now 1913, we're in the midst of all the discoveries that we talked about regarding the atomic model and in nuclear discoveries and so on and so forth. And he was able to determine exactly what the atomic number was based on that X-ray diffraction pattern. He arranged the elements in order of increasing atomic number now, rather than mass, the way Moseley did. And he was able to fix several discrepancies in Mendeleev's periodic table that existed because several elements' properties were not in line with their location according to their mass. All right. For instance, as I look at the periodic table here, tellurium number 52 and iodine number 53, tellurium actually has a greater mass than iodine has. So according to Mendeleev, those two elements would have been switched, which doesn't make a lot of sense, because it didn't make a lot of sense to him either, because iodine shares properties with the other halogens, fluorine, chlorine, bromine, and so forth, and tellurium shares properties with selenium, sulfur, and oxygen, the elements in that particular column. And so, but yet by mass, he had them where he thought they should go. But Moseley, in determining atomic numbers, fixed that discrepancy and got tellurium and iodine in the correct place. There were several other elements scattered throughout the periodic table where that was also true. So the atomic number thing really helped bring everything into line as it looks right now. So because of his research, the periodic table was revised to what it is today, that according to periodic law. The elements' physical and chemical properties are a periodic function of their atomic numbers. Okay, what's an atomic number tell us? Well, it tells us how many electrons it is, which directly relates then back to what we've been talking about, quantum numbers, orbital diagrams, and electron configuration ultimately. And also that atomic number tells us the number of protons in its nucleus, which is also very important as well. Little historical note here, Moseley was tragically killed on the front lines of World War I. All right, World War I broke out in 1914. Moseley was doing his work right during this time, and he was drafted into the war. Great Britain was heavily involved in World War I, and as other male soldiers of the time, he was sent to the front lines of battle, and he was killed. He was only 28 years old, and he had really just begun his work with the periodic table. And as a result of his death, not only the British government, but basically all other governments decided, hey, these scientific guys that can really help us develop things, maybe that would help contribute to the war effort, maybe we should be having them work in a research lab to help our cause, rather than send them to the front lines of battle. And that is true even today. So it's not that scientists don't serve their countries. They do, but they do in ways other than, going to the front lines. And so the periodic table. Okay, we're going to just quickly end with this here. So there are 7 horizontal rows or periods Why are there only 7? Well, we've discussed that. All right. Remember, these horizontal rows tell us the outermost occupied energy level that applies to that particular row. Every element in that row has its outermost electrons in that particular energy level. So and then the vertical columns are called groups or families. All right. So let's take a look at that. All right. So let's pull up our periodic table here real quick. Go. There it is. All right, so again, the periods are the horizontal rows. So 1, 2, 3, 4, 5, 6, 7. And again, as we've said before, those are the periods. And those represent every element in that period or horizontal row shares its outermost occupied energy level. So row 1 is just hydrogen and helium. Of course, they're 1s1, 1s2. Their outermost occupied energy level is level 1. The next row 2, lithium to neon, 2s2p, outermost energy level, level 2. Next row 3, sodium to argon, 3s3p, outermost energy level, level 3. 4, we have 4s, 3d, and 4p. Outermost occupied energy level, level 4. All right, and so on, and so on, and so on. So those are the periods, the horizontal rows. The vertical columns are called groups or families. All right. So what do all elements in a group have in common in regard to electron configuration? Well, this is group 1A and 2A next to it, the S group. The S block, 1A and 2A. We're going to jump across the center, the transition metals here, the center block, the D block. Remember, this is the D block. We're going to jump over here to the P block, and the A's continue. 3A, 4A, 5A, 6A, 7A, and 8A. There's also another way of numbering the columns. They just go 1 through 18 all the way across. And that's fine. I don't really like that method because the way they're named here really has significant meaning. And let's talk about that a minute. So all of the elements in 1A, remember they end with S1. Hydrogen, of course, is 1s1. Lithium ends 2s1. Sodium ends 3s1. Potassium ends 4s1. We've talked about that before. So this being their outermost energy level, the period that they're in, the group that they're in tells us how many electrons there are in that outermost occupied energy level. So for group 1A, that would be 1. Group 2A, that would be 2. Group 3A, so look at boron. Boron is 1s2, 2s2, 2p1. So it has its outermost occupied energy level is level 2. It's in row 2. But now how many electrons does it have in that outermost occupied energy level? Well, it's 1s2, 2s2. Let's write that. 1s2, 2s2, 2p1. Its outermost occupied energy level is level 2, and it has 2 plus 1, 3 electrons in that outermost occupied energy level. All right? Hence the name 3a. 3 outermost electrons. We have a name for those electrons. I'll bet you might remember it or heard it before, and those are called valence electrons. Valence electrons. So in 4A, so carbon is 1s2, 2s2, 2p2. All right. It has 4 electrons in that second energy level, its outermost energy level. So 4 valence electrons. 5A, 5, 6A has 6, 7A, 7. And 8A has 8, except, of course, for helium, which only has 2 because it's, number one, it only has 2 electrons. Its outermost occupied energy level is full, but it doesn't have a p orbital, so it's only 2 rather than 8. Okay? So brief little rundown there on the names. So the rows, the horizontal rows are periods. they tell us the outermost energy level for each element in that row that where its electrons are located, its outermost one. And then the group 1A through 7A, or sorry, 1A through 8A tells us how many electrons there are in that outermost occupied energy level. Okay? I think that's probably as far as we need to go today, because that should allow you to get your assignment completed. Again, the assignment is periods, groups, and electron configuration. It shouldn't take you all that long. Most of it's review, plus a little bit of what we talked about here today. We'll continue on with our study of the periodic table tomorrow. All right. So until then, this is Mr. Keister signing off. So take care, everyone. Stay safe. Keep working hard. Stay focused. And I'll catch you next time. So long.